Okay, everyone. So welcome to the analysis and optimization session. I'm Fredrik Kjolstad from Stanford University, and our first speaker will be Tetsuro Yamazaki, who will be talking about collecting cyclic garbage across foreign function interfaces, and who takes the last piece of the cake. Please.
Okay, hello. Thank you for the introduction. My name is Tetsuro Yamazaki from the University of Tokyo. Today, I will talk about collecting cyclic garbage across foreign function interfaces. So one day, I was developing a GUI application in Ruby. However, I did not know a good graphics library, so I decided to use the DOM library in JavaScript via a foreign function interface over HTTP from Ruby. So my program running on the Ruby VM accessed the JavaScript library running on a web browser. Because I was familiar with the DOM library, and I also hoped the Stack Overflow helped me. However, this FFI from Ruby to JavaScript caused a problem. So this is a Ruby program. I used JS call, which is an FFI library for Ruby. The range variables hold references to JavaScript objects. They are called through the FFI. For example, in the third line, jscore.exec sends character string document over HTTP, and it is evaluated as a JavaScript expression on the browser, and a reference remotely pointing to the document object on the browser to Ruby. However, this program makes cyclic garbage, and it causes memory leak, because naive FFI implementation does not collect cyclic garbage. An event callback function makes, an event callback function attached to the button HTML element makes cyclic garbage. And this program is a callback function attached to a button element. The callback function so this callback function is written in Ruby, and it refers to the button HTML element colored orange. And the button HTML element refers to this Ruby function. So there are a cycle. Naive FFI implementation does reference counting garbage collection because Ruby and JavaScript garbage collector do not trace remote references. So to collect such cyclic garbage, FFI must deal with two types of liveness, local liveness and global liveness. An object is locally live when it is reachable from the root without considering remote references. It considers only orange references in this figure. Similarly, an object is globally live when it is reachable considering remote references. It considers these orange references. Local liveness and global liveness must be consistent, otherwise a memory leak occurs or the VM crash. this is our technical goal. To avoid memory leak, we must collect cyclic garbage. Maintaining them is not easy because both Ruby and JavaScript have their own garbage collectors running independently. We do not modify JavaScript's garbage collector or VM because we want to use an off-the-shelf web browser as it is. We modify only Ruby's VM. We assume that remote references are not so many because we just want to use a foreign library. Ruby and JavaScript programs are supposed to be loosely coupled. So this is our proposal. Our proposal is Refgraph GC. It is a coordinator of garbage collectors in two languages for reclaiming cyclic garbage across a foreign function interface. It coordinates local and global liveness by copying a reference graph in Ruby to the heap space in JavaScript. The graph is compressed before being copied. So an advantage of our approach is it does not modify the collector in JavaScript. It modifies only Ruby's collector. Because JavaScript's garbage collector can inspect the Ruby heap space by traversing the copied reference graph. So let me show Refgraph GC by an example. Now, the left-hand side is Ruby, and the right-hand side is JavaScript. All objects reachable from the Ruby root, A, B, C, and D, are live, and all objects reachable from the JavaScript root, E, is also globally live. The other object, F, G, H, I, J, are garbage, and they are cyclic. First, Refgraph GC compresses an object reference graph in Ruby and copies it into JavaScript. For example, so for copying this graph, the Ruby VM must be modified. In this figure, double line arrows are edges in the copied graph. After copying, Refgraph GC runs garbage collection in JavaScript. The object G and H will be reclaimed. After that, everything goes back. Ruby objects F, I, and J have not been reclaimed yet, but now they are cyclic, and Ruby's garbage collector can collect them. We implemented Refgraph GC on the Ruby VM without modifying JavaScript's runtime. However, our first implementation could not reclaim all cyclic garbage. This is because our algorithm assumes that we can run JavaScript's full garbage collection just after copying a compressed reference graph. It is not always possible to control when garbage collection runs. So we improved Refgraph GC. Now, Refgraph GC resumes mutator thread just after copying a compressed reference graph, but before JavaScript GC finishes. Note that a mutator thread can change an object reference graph in Ruby, and a copied graph in JavaScript must be consistent with the original graph. So let me show an example. Again, the left-hand side is Ruby, and the right-hand side is JavaScript. First, a reference graph in Ruby is compressed and copied into JavaScript. After copying a compressed reference graph, a mutator thread in JavaScript in the right-hand side may remotely call the method on the object B in the left-hand side. And it may pass a reference R pointing to the object D as an argument. So then the mutated thread may create the reference R prime pointing to D from B. So the path from A to Z is created, A, B, D, E, F, G, but no corresponding edge is in the compressed reference graph. So what is the problem in this example? After passing a reference to D as an argument, a mutated thread in JavaScript may raise a reference Q pointing to C. Since the object C is not reachable from the JavaScript root, JavaScript garbage collector will reclaim C and G. So C and G are reclaimed, but G is still alive. A mutated thread can access G by following A, B, D, E, F. So it is a problem. To avoid this problem, we use send barrier. The send barrier prevents inconsistency between the graphs. When the reference R pointing to D is passed or sent from JavaScript to Ruby, the send barrier detects this. A compressed reference graph is eliminated, and a pin on the object G is restored. We can find G simply by following edges starting from C in the compressed reference graph. This pin on G protects the object G from JavaScript garbage collection. So we did experiments. So please read our paper for details. The experiment shows that our algorithm works well. It could collect cyclic garbage. And we also experimented on execution time. The overhead due to Refgraph GC is mostly small, comparing to the whole execution, or comparing to the Ruby garbage collection. And the size of compressed reference graph was relatively small. It did not exceed 2% of the whole heap space. And this is our related work. Cross-component tracing collects cyclic garbage across V8 JavaScript engine and Blink HTML renderer. The approach modifies two garbage collectors, but our approach modifies only one collector. Graph truffle is also related work. It allows two languages to run on the same VM. Our approach is for two languages on different VMs. So this is summary. We proposed Refgraph GC for collecting cyclic garbage across two languages. It is done by compressing and copying an object reference graph to another language. We did not modify both garbage collectors to implement Refgraph GC. We modified only one garbage collector, Ruby's one. Our target was foreign function interfaces. In our setting, two languages are running on separate processes. So that's all. Thank you for listening.
So if you have a question, please just step up to the microphone.
Hi, I'm Sam Westrick from Carnegie Mellon University. Great talk. I was curious, when you compress the graph on the Ruby side, do you need to do essentially a full garbage collection pass on the Ruby side in order to traverse the whole graph in order to do that compression?
So question is about how do the algorithm compresses the graph?
Yeah, that's right.
So to compress the graph, we have to traverse all the graph. And it cannot be done in a single pass. We traverse the heap space for each incoming remote reference from JavaScript to Ruby. But we found that first, we mark all objects reachable from root. Then we can skip traversing objects if it is reachable from root. So the total traverse time is not so long.
Great, thank you.
Thank you.
Hi, Andrei Lasko from King's College London. How extensible is this work for any other two pair of languages?
I'm sorry, say again, please.
So in the presentation, you talk about Ruby and JavaScript. Can I use any other two languages with this idea?
So the question is about is our algorithm is only for Ruby and JavaScript. So the algorithm is abstract, and I think we can use it for other settings. But it assumes that both collector does tracing garbage collection. So, for example, reference counting is not very good. It may cause some other problems.
Okay, thank you.
Thank you for question.
Okay, let's thank the speaker then.